Hi all, welcome to the lecture series on Aerospace Propulsion. I am Mr. Manideep Gupta, Assistant Professor, Department of Aeronautical Engineering from MLR Institute of Technology. So today the topic which we are going to discuss is orbit, orbital velocity, orbital period. Let us go into the overview of today's presentation. Today we are going to discuss about orbit, orbital velocity and orbital period. The basics regarding the motion of bodies in the space. So coming to the orbit. So what is actually an orbit is? So an orbit is an irregular repeating path that one object in space takes around another one. So it is a regular path followed by an object. Suppose if you take this is an earth, okay, and there is a mass of m, it is moving in a circular path. So regularly this object moves in the same path with the same time. Then that particular path, whatever the circular path, this path is called as orbit. This path is called orbit. So an orbit is a regular repeating path that one object in space takes around another. One object will rotate on another in a regular path. Then the path followed by the object is called orbit. So the two forces, in order to make the object to rotate in the same path, to move in the same path, there is one law. Okay, one law to be satisfied, that is the two forces must be equal and opposite for the body. Suppose if the body is rotating here, whatever the body force is acting on this. So if you see here, there is a centripetal force that is due to the earth gravitational force acting towards the center, and there is centrifugal force which is acting away from the center. Okay. Whenever any body rotates, moves in a circular path, it will have centrifugal force. It will have centrifugal force and centripetal force. Okay. So if the centripetal force and centrifugal force both are equal, then only the object can rotate or move in the same path with the same radius. Okay. So this is one condition for the bodies to move in the orbit. So if you see here, capital G into me by r square is the centripetal force acting toward the center. Okay, the same body I am considering here. The same body I am considering here. So this is the centripetal force and the centrifugal force m omega square r. So this is m omega square r. So this is the basic condition for any object to rotate or to move in a particular orbit. So here, if you observe here in this equation, here capital G is a universal gravitational constant, m is the mass of the body, me is the mass of the earth, r is the radius of the orbit, right? And here omega, and here the same m is the mass of the object, omega is the angular velocity, and r is the radius of the object. So if you see here, if you see this equation, m and m will get cancelled, and here r will go down here and it will become r cube. It will become r cube. And finally, if you write an equation for the omega, that is angular velocity in this equation, then the equation will be capital G into me by r cube under root. So omega equal to under root capital G me by r cube. So where G is universal gravitational constant, me is the mass of the earth, and r is the radius of the orbit. So like this we can calculate the angular velocity of the object so that it can stay in a particular orbit. Suppose if you want to send, if I want to send a particular, suppose this is an earth, okay, I want to send an object into an orbit which is at a 5000 kilometer radius. Suppose 5000 kilometer radius, just for example, I want to send an object to a 5000 kilometer radius. So how much angular velocity to be maintained? How do I calculate? So I can calculate the angular velocity to be maintained by my object, so that the forces acting, that is centrifugal force and centrifugal force, both will match. Okay, when I maintain the angular velocity according to this equation, then the body will continuously rotate in the same orbit. So like this equation will help us to know what is the angular velocity that a object to be maintained, so that it will maintain in a particular orbit. Okay, so this is angular velocity. Okay, this is angular velocity, and we know that we can get the equation of linear velocity from the angular velocity. Angular velocity units are what? Radians per second. And if you know the linear velocity v is meters per second. Okay, angular velocity is nothing but the angle made by the object from one position to another position divided by the time taken by the object from one position to the second position. So that is angular velocity, radians per second. If you want to calculate the linear velocity, then v is equal to, there is a relation, that is v is equal to r omega. So if you apply omega, this equation omega here, then you will get linear velocity v. Okay, let us find v now, linear velocity of the object to be maintained, that is tangential component. Linear velocity is nothing but the tangential component of the object velocity. So now I am going to find the linear velocity of the object. So if I substitute v is equal to r omega, if I take the equation v naught is equal to r omega, and if I substitute omega here, then what happens? This will become r into under root capital G me by r cube. Suppose if I send this r into the root, then it will become r square, and r square and cube will get cancelled. Finally, you will get under root capital G me by r. So v naught is equal to what? Under root capital G me by r. So this is nothing but called as linear velocity of the object in the particular orbit, and this linear velocity is nothing but called as orbital velocity. Whatever the linear velocity v naught maintained by the object in a particular orbit is nothing but called as orbital velocity. So the equation for orbital velocity is under root capital G me by r. What is the equation for angular velocity? Capital G me by r cube under root. Okay, so this is orbital velocity. So finally what is the definition of orbital velocity? The velocity, the linear velocity v naught, that is going to be maintained by an object to stay in a particular orbit, is nothing but called as orbital velocity, and this is the equation for orbital velocity, and the units are meters per second or feet per second based upon the system in which we are calculating the quantity. For example, if a spacecraft orbiting the earth at a height 200 km. So what is the orbital velocity? How do we calculate the orbital velocity? So we can calculate the orbital velocity with the help of this equation. Now we will calculate that. So substitute the equation here. So what is r here? Radius of the orbit. What is r? Radius of the orbit. So if you substitute, I want to calculate the orbital velocity about the earth. So I will consider, okay, here already we have, right? So I will consider again. So this is earth having some radius. What is radius? Just a second. Okay, this is earth. Okay, and this is the center of the earth, and this is the radius of the earth, and the orbiting body. This is the orbit. Consider this is the orbit. And what is this distance? This distance, he said, it is 200 km. Okay, this is the radius of the earth, right? So what will be the orbit, radius of the orbit now? What will be the radius of orbit? So radius of the orbit r is equal to radius of the earth plus altitude h of the object. So that is what substituted here. Capital G me under root capital G me by, in place of r is equal to re, radius of the earth plus height of the object. So this is nothing but the radius of the orbit. Okay, but here he given altitude of the orbit. So that's why we have to take r is equal to re plus h, that is radius of the earth plus height of the object. So if you substitute these values here, then what is capital G? 6.67 into 10 to the power of minus 11, and mass of the earth is 5.974 into 10 to the power of 24, and radius of the earth is 6380 kilometer, 6380. Okay, and the next height of the object is how much? 200 kilometers. Okay, 6380 kilometers, 200 kilometers. So as I have to convert this kilometers into meters, so I have multiplied this with 10 to the power of 3. Then this kilometers will turn to meters. Okay, so finally I will get 7760 meters per second. So if I convert this meter per second into kilometers, it is 7.76 kilometers per second. Is the orbital velocity need to be maintained by an orbit which is at 200 kilometer height. 200 kilometer height. So if it is 200 kilometer height, then the orbital velocity V0 should be 7.76 kilometers per second. Just imagine how much orbital velocity to be maintained for an object at a height of 200 kilometers, 7.76 kilometers per second. So this is a small problem on orbital velocity. Next, if you analyze the orbital velocity, how the orbital velocity is varying with respect to the altitude. So if the orbital velocity decreases as the radius of the orbit increases. If you observe the formula, what is the formula? V0 is equal to under root capital G me by R. So here if you observe, V0 is inversely proportional to the radius. V0 is inversely proportional to radius. That is why orbital velocity decreases as the radius of the orbit increases. So R increases, V0 value decreases, inversely proportional. And the orbital velocity is seen to decrease from a value of about 7.9 kilometers per second at the Earth's surface, about 2.66 kilometers at a height of 50,000 kilometers. Suppose if I want to make an object rotate in a repeating path from the Earth's surface, just above the Earth's surface, then the object need to maintain a velocity of 7.9 kilometers per second. Then it will continuously rotate in a orbit which is just above the Earth's surface. And if you go to the 500 kilometer altitude orbit, 50,000 kilometer altitude orbit, then the velocity need to be maintained is 2.66. That means the orbital velocity is decreasing here from 7.9 to 2.66 as radius is increasing. Okay, and here you can also observe the graph how the orbital velocity is decreasing with respect to altitude. So this is at a 1 kilometer altitude, 10 kilometer, 100 kilometer, 1000, 10,000 and here 1 lakh kilometer altitude, not radius. Okay, and you can observe orbital velocity is gradually decreasing here, right? So this is about orbital velocity. So the next topic is orbital period. So what is orbital period? The time period of revolution for one orbit is nothing but called as orbital period. The time period for one revolution in a particular orbit is called as orbital period. So how do we calculate the orbital period? Orbital period is nothing but the time taken, right? So time is equal to distance traveled by velocity. So what is the distance covered by the object in one orbit? 2 pi r. 2 pi r is the radius of the orbit, like perimeter of the orbit. And what is the velocity of the object in the orbit? V0, orbital velocity. Then if you substitute here 2 pi r by V0, and you know the equation for V0, that is under root capital G me by R, and substitute V0 here, then you will get 2 pi into under root R cube by G me. So this is the equation which we will get for the orbital time period. So by this equation we can calculate the orbital time period, and this can be also written as, we know omega, right? So it can be also written as 2 pi by t is equal to 2 pi by omega in terms of angular velocity. It can be also written as 2 pi by omega. If you want to consider the angular distance, this 2 pi is nothing but the angular distance that is covered by the object, that is 2 pi radians in one rotation. Okay, and the velocity is angular velocity omega. So like this we can calculate time period with respect to linear velocity and with respect to angular velocity. So if I substitute the values, like capital G is constant, and if I want to calculate time period for a orbit which is about the Earth, then me, mass of the Earth, is constant. So if I substitute these two values and 2 pi, then this equation will be simplified to 0.304 into 10 to the power of minus 6 r to the power of 3 by 2 seconds. Next, if you observe this graph, this is a graph explaining the variation of orbital time with height of the orbit above the Earth and how the orbit time period is changing. Simply, if you see here, if you observe this equation, t is directly proportional to the r to the power of 3 by 2. Sorry, 3 by 2. That means as the radius increases, the orbital time period also increases. So the time period for one revolution increases as the height of the orbit increases. Next, if you just analyze this graph once, the time period increases about 1.4 hours at a height of 100 kilometers and 35.7 hours at a height of 50,000 kilometers. So if you go to the 100 kilometer altitude orbit, the time period is 1.4 hours. So the object takes 1.4 hours to complete one revolution. Here, if you go to the 50,000 kilometer altitude orbit, the object will complete one rotation in 35.7 hours. 35.7 hours, which is more than 24 hours. More than 24 hours. That is the Earth rotation time. Like this. Here you can observe. Here it is increasing. Orbital time period is increasing with the altitude. And if you go on like this, at particular time, at particular altitude, this orbital period is 24 hours. What is that? 24 hours at a particular altitude, right? This is the height where the orbital period is equal to 24 hours. What is this 24 hours? Nothing but the Earth rotation time. So at particular altitude, the object also takes as 24 hours as the Earth rotation time. That particular orbit is nothing but called as geosynchronous orbit. So at 35,786 km above the Earth, the time for orbit is 24 hours, which is equal to the Earth rotation time. Okay, so this particular orbit is called geosynchronous orbit. We discuss about the properties of the geosynchronous orbit in the next lectures. So these are the topics which we are discussed today, right? So finally, orbit, orbital velocity and orbital period. And if you see here, orbital period, what happens to orbital period? Orbital period is directly proportional to the radius. If radius increases, orbital period increases. And what about the orbital velocity? Orbital velocity is inversely proportional to the radius. So if radius increases, orbital velocity decreases. Right. Coming to the summary of today's presentation. So today we have gone through the definition of orbit, what is orbit, and what is a condition. What is the condition for an object to stay in a particular orbit, and how much orbital velocity need to be maintained for an object to at a particular height, and what is the time taken for the object to complete one rotation in orbit, that is orbital period. So these are very, very important parameters need to understand in the analyzing the motion of bodies in the space. Thank you.